Power is the rate at which energy is transferred. Power determines the brightness of an LED or bulb. We can calculate the power dissipated through an LED by multiplying the potential difference across the LED by the current strength through the LED. Let's compare circuits 2 and 3. Predict which LED will shine brighter, the one in circuit 2 or the one in circuit 3. Pause until you've done that. To help us to think about this, let's remove the meters. They don't affect the circuit in any way, they just take measurements. But it helps if they're gone, like this, because then it's easier to think about what is really important in the circuit. So how do these two circuits differ? The only difference between them is that circuit 2 has a 22K resistor in the place of circuit 3's parallel section of two 22K resistors. So what does adding this resistor, this 22K resistor, to circuit 2, because that's in effect what we've done. You take circuit 2 and add a 22K resistor, then you end up with circuit 3. So what does that do to the LED? How does the presence of this extra parallel section in circuit 3 affect the LEDs? Now, whenever you work with parallel circuits and you want to compare a parallel circuit to another parallel circuit or to a series circuit, then to help you to think about the situation better, you should replace the parallel combination with a single resistor that has equivalent resistance, that has the same resistance as the two in parallel combined. And that's what I've done here. Both of these circuits are actually the same circuit. They are both circuit 3. We can call the top one circuit 3 because that is exactly as we saw it just now, and we can call the bottom one circuit 3 equivalent because it is equivalent to circuit 3 even though it might not look at first glance exactly the same as circuit 3. It has the same effect as circuit 3. So how do these compare? Everything is the same about them except that this parallel section here has been replaced with a single resistor so that now we have a series circuit, and this single resistor has the same resistance as that parallel combination has. What is the equivalent resistance of two 22K resistors in parallel with one another? Whenever you place two resistors of the same value in parallel with one another, their equivalent resistance is half of each of them. Why? Because it's like you've made a double as thick pipe, so it's double as easy to go through now, and so you've halved the resistance. We can do this the long way as well if you like. We know that R equivalent for two resistors in parallel with one another is equal to the product of the two resistors divided by the sum of the two resistors. So the product is 22 multiplied by 22, and the sum is 22 plus 22. And if you do that on your calculator, you find 22 multiplied by 22 is equal to 484, and divide that by 22 plus 22, which is 44, and what do you get? 11. So here I have circuit 2 compared to circuit 3 equivalent. So now we have two series circuits. It's a lot easier to compare two series circuits with one another. We notice that in both cases there's a 9-volt battery supplying 9 volts. So let me draw the V for 9 volts this size. I'm trying to draw them the same size as one another. That is what is supplied, and that must be shared between the two resistors in each case. So if we were to add the voltage across the 22K with the voltage across the LED here, it must add up to 9 volt. And if we add whatever the potential difference is across the 11K here with that across the LED, it must also add up to 9 volt. So in both cases, there's 9 volt to be shared between two components, a resistor and an LED. How is it going to be shared? It will be shared in the same ratio as the ratio of the resistances in the circuit. For simplicity, let's say that the resistance of the LED is the same for both circuits. So I'm trying to make those two R's the same size as one another. However, the resistance of the resistor that the LED is with is not the same for the two circuits. In circuit 1, that's 22K, whereas in circuit 2, that's half of that. Now it's important here to realize we're not actually comparing the 22 with the LED, the 11 with the LED. That we're not sure about. The point is we're comparing these two resistors with one another when these are constant. And why does that help us? Because the ratio of the resistances is what determines the ratio of the potential difference. And in circuit 2, the ratio lies more heavily on the 22K's resistor than it does on the 11K for circuit 3. Or put another way, the LED in circuit 2 is with a very greedy partner. And that greedy partner is going to take a big chunk of the supplied voltage. Lots of the supplied voltage is going to go to that greedy partner, more so than is in the case of circuit 3's 11K resistor. And that means that not so much is left over for the LED in circuit 2, whereas more is left over for the LED in circuit 3, because the LED in circuit 3 isn't with someone that's so greedy, whereas the LED in circuit 2 is with someone who is very greedy. Now let's speak about current strength. Where's the current strength going to be greater? Through circuit 2 or circuit 3? The total potential difference is the same in each circuit, so the pressure pushing the charge to flow is the same. But the total resistance of circuit 2 is greater than the total resistance of circuit 3. And so it's more difficult for the current to flow through circuit 2 than it is for current to flow through the circuit in circuit 3. There's a higher current strength through every part, including through the LED, through circuit 3 than through circuit 2. So let's now only focus on the LEDs. And we know that power is what determines the brightness of the LED, and power is equal to potential difference multiplied by current strength. We can see that in circuit 2 we have a low potential difference across the LED and a lower current strength through the LED. Whereas in circuit 3 there's a higher potential difference and a higher current strength through the LED. So the product of the two, V times I, is going to be a small number in circuit 2 and a bigger number in circuit 3. The power is the rate at which energy is converted into light and heat. So that means that here there's a greater rate of energy conversion, circuit 3, than in circuit 2. So circuit 3 is going to be brighter than circuit 2. Remember, of course, this is circuit 3 equivalent, but that is circuit 3. Circuit 3 equivalent is circuit 3. Here I have the circuits. It's dark on purpose so that we can see the LEDs shining nice and clearly. This is circuit 2. Take a look at how bright it is. Can see that it's not very bright, and let's quickly compare it to circuit 3, and you can clearly see circuit 3 is brighter than circuit 2 because the power dissipated through the LED in circuit 3 is greater than in circuit 2. So more electrical energy is being converted into light energy per second in circuit 3 than in circuit 2.